Alright everyone, we're going to do some science. So in this video I'm doing an SN1 reaction and also including the mechanics of an energy diagram because I think it's important to see how one relates to the other. So we're going to do the reaction first and then tie all of that in with the energy diagram at the end. So this is an SN1 reaction. We're going to go a little bit faster than the last video because SN1 basically looks the same every time. So in the first step, one of the lone pairs from the oxygen grabs onto the hydrogen, and then this bond breaks. So we have chlorine in our solution that's just going to float around until we need it later. And we're going to redraw our molecule, except now our OH has two hydrogens on it, which is what causes it to have a positive charge. And then after this step, the electrons in this bond are given back to the oxygen, and now we have water also floating around in our solution. So we redraw our molecule, and because the water left, now we have a carbocation, and we're going to represent our carbocation as planar because it's an sp2 carbon, so that means it has three substituents, and it lets everybody know that you also know that there are three substituents on the carbocation. So at this point in the steps, we decide whether or not our carbocation is as stable as it could be by recognizing if it's secondary or tertiary. And our carbocation is secondary because it has two non-hydrogen substituents. So we're going to see if we can move anything around in our molecule in order to make it tertiary. So right now it's secondary. And we're going to look around. We can only take off things that are on carbons adjacent to the carbocation. So that means that we can take stuff off of this carbon or this carbon. And we wouldn't move this methyl group or this ethyl group. We wouldn't move the bromine. We wouldn't move this ethyl group because then we would just be right back where we started with the secondary carbocation. So instead, we could move, use a different color, we could move this hydrogen or we could move this hydrogen. And since we have two options and we know that in our big bucket of water or whatever we're doing with our reaction, there are now two tertiary carbocation options. So we have to draw both of them and then draw the products for both of those. So this one's going to be for, let's see, this hydrogen, and then we're going to do another carbocation with the red hydrogen. So the top one is with this green one. So if we move this hydrogen onto the carbocation, that means that our carbocation will now be where that hydrogen was. So we're going to redraw our molecule. Bromine is still there. And now this carbon has two hydrogens. You don't have to draw those hydrogens because we know that they're there, but it's good to just recognize that you know where that hydrogen went, and now our carbocation is right here. So now we're going to draw the new molecule for the other hydrogen that happens. So we get this. Oops, sorry. Okay, bromine, hydrogen, hydrogen. Okay, cool. And this is our carbocation for this one. So now we have two carbocation options, and we know that they're both tertiary because they have three non-hydrogen substituents. And this is the part where we check for stereocenters. So when we add our chloride ion that's floating around in our solution, are we going to form a stereocenter? For this first carbocation, we are going to form a stereocenter because we're going to have, excuse me, we're going to have a carbon that has four different substituents. So that means that when I draw my product, I'm going to have to represent that I know that there is a stereocenter right there. So that means I have to draw wedges and dashes from my chlorine. And we're going to do that same thing for the other molecule, the same thought process. When I add my chlorine to this carbon right here, I know that I'm going to form a stereocenter because I will have a carbon with four different substituents. So this is just what we're forming, like this. But I know that I'm going to have two molecules here because one of them, the chlorine's going to be a wedge, the other one's the chlorine's going to be a dash, and I'm going to have two molecules right here, one where the chlorine's going to be a wedge and one where the chlorine's going to be a dash. So now we're going to draw out all of those products. This is going to be where I'm going to draw the top part, and then this is where I'm going to be going to draw the bottom part. So for this top part, I have, chlorine, And I'm going to put the ethyl group on my dash and then redraw it. Bromine, chlorine, ethyl. And we're going to do the same thing for the other one where I have bromine, chlorine, and here, same thing, except it's just going to be flipped around. So I have bromine and chlorine. And if all of that went super fast, then I totally recommend watching my other video. I'm not trying to promote myself, but I did go kind of fast in that reaction, so if anything looks a little bit unclear, just watch the other video. So now that we're done with our reaction and we have all of our products, now we're going to draw an energy diagram representing what happened in this reaction. So an energy diagram just lets us know basically how the energy changes throughout the course of a reaction. So that means that on the x-axis we're going to have time. It could be seconds, milliseconds, it could be hours, days, because chemistry can take forever. It could also take a couple seconds. So on the y-axis we're going to have energy. So down here we're going to have low energy, and up here we're going to have high energy because y-axis goes up. So let me see. This chunk is the first step of our reaction, but our starting molecule right here is pretty stable, so it's got a low energy, pretty happy by itself. And then once I'm going to put COH, representing that is our first molecule. And then once it reacts with the hydrogen, now this oxygen has a positive charge, so that means that probably has a little bit higher energy than the last molecule, but not that big of a difference. I'm going to draw just like a little bit above here, because we know that this oxygen has a positive charge. And from here to here, we're going to draw our little humps. Right here means transition state. That's where bonds are breaking and forming. And at these little troughs right here, these are the intermediates. We draw the intermediates throughout the reaction. Like this is an intermediate, this is an intermediate, intermediate, and then obviously we keep going on the other side. But the transition state is where the bonds are breaking and forming. So in this first step of the reaction, the oxygen is forming a bond with hydrogen, and our hydrogen and chlorine bond is breaking. So it's really good to recognize what's forming and what's breaking, because that helps us also identify how to put all that stuff into our energy diagram. So for our second chunk, this is a one molecule, one step chunk, and this is actually the rate determining step, because at this part of the reaction we're forming our carbocation, and we know that carbocations are really unstable. God does not like carbocations, so that's why after we form our carbocation over on the other side, we're going to have a very high energy molecule, and this high energy molecule is the carbocation right here. So I'm going to draw my little hoop that goes all the way up here, and the transition state at this chunk is showing that this bond right here is breaking, but we're not really having any bonds forming, because this water molecule that falls off and ends up in our solution is the only thing that's really happening. That bond is breaking, and that's pretty much it. So normally this reaction has 3 steps, where the OH grabs onto the hydrogen, and then it's positively charged. It falls off as a carbocation, and then we stick our halide onto there. It could be bromine, chlorine, iodine, and then we have a happy molecule. However, this reaction shows shifting, so that means that we have kind of like a step 2.5 in there, where we're going from a secondary carbocation to our tertiary carbocation options. So going from here to here, the bonds that are breaking and forming is us moving the hydrogens for the shift. So this bond is breaking, but it's also forming right here. And then for the other carbocation option, this bond is breaking, but it's also forming right here. It doesn't really matter which hydrogen is which, because they're both hydrogens. And we know that tertiary carbocations are more stable than secondary carbocations, which is why we did the shift in the first place, because God likes tertiary more than secondary. So that means that our tertiary carbocation molecule is going to be lower in energy, more stable than our secondary carbocation. So I'm going to put my tertiary right here, keep my little thing going. And then after my tertiary carbocation forms, that's when our chlorine gets stuck onto there, and then we have our happy molecules that are down here. We have 4 major products in this reaction. So now when I draw my final product, I'm going to put it basically right back down here where we started, and I'm going to put CCl or CBr or Ci if it's iodine, letting me know that what I'm forming is an alkyl halide. What I started with here is an alcohol. We have an alcohol, and then we have a positively charged oxygen, which falls off, and then we have a secondary carbocation. we did a shift to form a tertiary carbocation, and then our chlorine, bromine, iodine, whatever sticks on there, and then we have our happy molecule at the end. And all of these little humps right here are transition states, and we went over how in this chunk the OH bond is forming, the HCl bond is breaking. Right here we just have one bond that's being broken, and it's this oxygen-carbon bond that once it leaves, it comes off as water. And then for our secondary carbocation shift step, step 2.5, our CH bond is breaking, but it's also forming because we have this CH bond breaking and then this CH bond forming. This CH bond is breaking and then this CH bond is forming. And then in our last step, the only thing that's happening is that we are forming a carbon-chlorine bond, and that's right here and right here. But instead of just drawing these two products, we had to represent that we know that after putting the chlorine on, we're forming a stereocenter. So that's why we have two answers for each of the carbocations, because when our chlorine sticks onto the carbocation, since we know that our carbocation is planar, like this, just pretend there's a little carbocation right there, that means that our chlorine could either come in from the top, pretend that that's from the top, or it could come in from the bottom. And if it came from the top, then that means that it would form as a wedge. And if it came from the bottom, then that means that it would form as a dash. And this is not a very good drawing because I'm not showing a wedge and a dash, I'm just showing the chlorine. But basically that's kind of the gist. So that's how we knew that we had to have more than just the two products that we drew at first up here, because we know that adding the chlorine onto this carbon and adding it onto this carbon will form a stereocenter. So that's kind of putting all the pieces together, doing an SN1 reaction, and then drawing the energy diagram for it. I totally recommend doing this by yourself so that you can actually know what's forming, what's breaking. It's super good practice, run through all the steps, and then actually being able to make an energy diagram lets me know, lets you know that you actually know what you're doing. So it's a very good test of your knowledge. Hope this video helped. I'm sorry that I went through the reaction kind of fast, but if I did go a little bit fast, just watch the other video, and then I feel like everything will all come together. So let me know if that helps, and comment if you have any questions.